Beneath the boundless night of the ancient Aegean, the sky blazed with stars unspoiled by smoke or city flame. The world was silent enough to hear the breath of the sea against the cliffs of Rhodes, silent enough to wonder if the heavens themselves were whispering numbers. There, more than 2,000 years ago, a man stood on the edge of the known world, measuring the unmeasurable, the distance between Earth and eternity. His name was Hipparchus of Nicaea, and though time nearly erased him, his mind became the compass by which the modern cosmos was drawn. He lived in the 2nd century BC, when Greece had scattered its intellect across a world ruled by Rome and illuminated by Alexandria. The torch of inquiry burned in scattered minds, mathematicians, philosophers, astronomers, each seeking to bind the heavens to reason. Among them, Hipparchus was not a poet of myth, but a craftsman of precision. He trusted no story that could not be measured, no pattern that could not be proved. Born in Nicaea, in what is now Iznik, Turkey, he would one day journey to Rhodes, a sunlit island whose clear skies made it one of the finest natural observatories of antiquity. Yet little else is known of his life. No marble statue, no surviving portrait. What remains is the echo of calculation. Fragments of his methods preserved by later thinkers, especially the great Claudius Ptolemy in the Almagest. From those scattered traces, we reconstruct the mind of a man who weighed the heavens like a merchant weighs gold. The sky of Hipparchus was not our sky of telescopes and equations, but it was sharper, clearer, alive with myth and geometry. To the ancients, the stars were gods in formation. To Hipparchus, they were coordinates. He did not seek divine prophecy in their motion. He sought their rhythm. When others sang hymns to the sun, he measured its path. When poets praised the moon's beauty, he charted its wanderings with disciplined eyes. In a world of belief, he became a world of proof. The mystery that first called to him was the changing sky. He knew, as every farmer and sailor knew, that the seasons drifted against the stars. The sun did not return precisely to the same place year after year. Somewhere in that subtle dislocation lay the hidden clockwork of the cosmos. To find it, Hipparchus needed more than curiosity. He needed instruments, records, and the courage to doubt tradition. He built armillary spheres, bronze rings that held the earth at their center and traced the great circles of the heavens. With them, he could measure the angular distance between stars and chart the apparent motions of the sun and moon. He compared his own observations to those of Babylonian astronomers, whose cuneiform tablets had captured celestial events centuries earlier. In that synthesis, Greek geometry married to Babylonian. Arithmetic, astronomy became a science. He discovered that the year measured by the sun's return to the same equinox, the tropical year, was slightly shorter than the sidereal year, measured by the stars. The difference was tiny, about 20 minutes. Yet in those minutes, the sky itself shifted over centuries. That insight led him to one of the most profound revelations in human history: the precession of the equinoxes, the slow wobble of Earth's axis that makes the stars drift imperceptibly over millennia. Imagine the courage it took to announce that the heavens were not fixed, that even the constellations themselves were slowly sliding. Across the dome of night, it meant that the cosmic order, which for centuries had seemed eternal, was in motion. The sphere of the stars, once thought divine and immutable, was alive with time. Hipparchus reached this conclusion through relentless comparison. He took the star positions recorded generations before, notably by the astronomer Hipparchus in Alexandria, and compared them with his own. He found that certain stars had shifted their longitude by about 2 degrees. That shift could not be blamed on error. It was systematic. Only a slow rotation of the celestial coordinate system could explain it. In that subtle movement, Hipparchus discovered the trembling of the Earth itself. No surviving writing of Hipparchus explicitly announces this discovery. His own treatises, including the commentary on Aratus and Eudoxus and on the length of the year, survive only in fragments, yet later authors testify to his insight. Ptolemy, centuries later, confirmed the precession at nearly the same rate Hipparchus had calculated. Such consistency across ages proves the precision of his instruments and the logic of his method. He did not merely measure the stars, he organized them. For the first time in known history, he compiled a star catalogue, perhaps more than 850 entries, noting each star's position and brightness. This was not poetry, but data, the earliest map of the heavens based on exact coordinates. From this lattice of light would later emerge the charts that guided explorers and navigators across oceans. He introduced a system of stellar magnitudes, ranking stars from the brightest to the faintest, visible to the naked eye. The same scale that astronomers, modernized but conceptually unchanged, still use today. In those classifications, the human eye met mathematics. Hipparchus's measurements were made from simple yet ingenious devices: a dioptra, like an early theodolite, for aligning stars, a gnomon for tracking the sun's shadow, and a water clock for timing lunar eclipses. From these, he calculated distances and sizes of the moon and sun more accurately than any before him. His estimate of the moon's distance, though not perfect, was astonishingly close to the truth, considering his tools were only wood, bronze, and intellect. He sought to model the moon's motion using combinations of circular paths, anticipating the later epicycles of Ptolemaic astronomy. He noticed that the moon's speed varied during its orbit, moving faster when closer to Earth. To account for this, he introduced an eccentric circle, offsetting the Earth slightly from the center of the lunar path. That small abstraction brought mathematics closer to nature. But perhaps his most enduring gift to the world was a new language of angles. To predict celestial positions, one needed to relate chords and arcs, to translate curves into numbers. Babylonian astronomers had used arithmetic tables. Hipparchus united them with geometry, creating the first known trigonometric table. He tabulated the lengths of chords in a circle of known radius, effectively founding the science of trigonometry. Centuries later, the Indian sign tables and Islamic astronomers' refinements would all trace their lineage back to that Greek seed planted on Rhodes. Each observation demanded patience beyond measure. Night after night, he returned to his instruments, adjusting, recording, comparing. He watched the moon slide against the backdrop of stars, noting its position to fractions of a degree. He timed eclipses, cross-checking Babylonian records to refine the moon's period. He turned mathematics into a time machine. Rhodes itself must have been his companion. The sea below, the perfume of pine, the gleam of marble temples under the constellations. The island's horizon offered him the perfect line for measurement. Here the Mediterranean became a mirror of the cosmos, the sea reflecting the heavens, the astronomer reflected in both. Hipparchus lived at a turning point. The golden age of Greek philosophy was fading, yet its intellectual seed had spread across continents. Alexandria's library was at its height, storing papyrus scrolls from every civilization of the known world. Scholars compared the mathematics of Greece with the star lists of Babylon and the calendars of Egypt. In that melting of ideas, Hipparchus stood as both heir and innovator. He did not destroy old systems, he refined them. When he noticed discrepancies between predictions and observations, he did not declare failure. He declared complexity. The cosmos, he realized, was not governed by perfect circles alone, but by subtle deviations. He built a model that could predict eclipses accurately, refining the Metonic cycle and introducing what later became the epicycle and eccentric theories of planetary motion. Though he likely never visited Alexandria, his work resonated through its halls. Later scholars cited his numbers as authority, his methods as foundation. Ptolemy, in the Almagest, called him the greatest observational astronomer of all time. Yet Hipparchus left no school, no disciples, no legend. He may have died quietly on Rhodes around 120 BC, his instruments dismantled, his star charts left to gather dust. For centuries, his name drifted like a faint constellation, visible only to those who knew where to look. His writings vanished, lost to fire, time, or neglect. Only echoes survived, preserved in the works of others. The modern rediscovery of his genius came in fragments. Ancient commentaries quoted his numbers. Early Islamic astronomers built upon his trigonometry. Renaissance scientists, armed with telescopes, still used his coordinate system. Celestial latitude and longitude anchored on the equinox. Then, in the 21st century, on the island of Kos, archaeologists uncovered a palimpsest, an overwritten manuscript that revealed hidden diagrams of star coordinates. These fragments, believed to reflect Hipparchus's lost catalogue, confirmed what scholars had long suspected, that he had indeed charted the heavens centuries before Ptolemy. The ancient precision still spoke, faint but unmistakable, across 2 millennia. If the story of Eratosthenes measured the earth, the story of Hipparchus measured the sky. Between them stretched the birth of geography and astronomy, 2 halves of the same quest, to locate humanity in space and time. When we look up today through telescopes or orbiting observatories, we are still following his method, comparing, calibrating, questioning. The universe has expanded, but the act of measurement remains a whisper from Rhodes. Perhaps that is why his name, though nearly forgotten, still matters. Because Hipparchus did what no myth could do. He found order without magic, wonder without illusion. He proved that truth itself could be divine if only one dared to measure it. The stars he mapped have shifted. Earth's axis has wobbled. Empires have risen and fallen. Yet the principle he uncovered, that even the heavens change, is the heartbeat of science. In the quiet of night, when the constellations drift above modern cities, the legacy of Hipparchus still turns with the earth, a silent motion through eternity. When the winds of Rhodes calmed and the last light sank beyond the sea, Hipparchus would raise his gaze once more. The sky was his manuscript, and every star a letter written in fire. He read that text through geometry, translating the movement of light into the language of number, distance, and proportion. To Hipparchus, the heavens were not infinite chaos, but a vast ordered diagram. Geometry, he believed, was the bridge between the mortal and the divine. Through it, the irregular became intelligible. The circle, to Greek thought, symbolized perfection, the shape of the gods, the orbit of the sun, the pattern of harmony. But in the measured heavens, the circle faltered. Planets wandered, the moon sped and slowed, eclipses came imperfectly timed. Hipparchus sought to restore harmony by explaining these deviations with geometry refined by observation. He began with the sun, using the gnomon, a simple upright rod casting its shadow on the ground. He measured the sun's altitude throughout the year. At the solstices and equinoxes, he noted the shadow's length, tracking the sun's north-south movement. By comparing these points, he determined the length of the tropical year: 365 days, 5 hours, 55 minutes, astonishingly close to modern values. Yet he noticed it was slightly shorter than the sidereal year. From this emerged the awareness of precession. He then turned to the moon, whose changing face fascinated both priests and sailors. Lunar eclipses offered him an instrument finer than any bronze ring. When the Earth's shadow slid across the moon, it became a cosmic clock, allowing him to measure the difference between solar and lunar months. By comparing eclipses recorded in Babylon with those seen in his own time, Hipparchus deduced the moon's period to within seconds of the modern figure. But his true mastery lay in modeling motion. He realized the moon's path could not be a perfect circle centered on Earth. Its varying speed demanded an offset, an eccentric orbit, or perhaps an epicycle, a smaller circle rolling along a greater one. This concept, elegant and predictive, would become the foundation of the geocentric models that ruled astronomy for the next 18 centuries. To compute such motions precisely, he needed a system for relating angles to chords. Here, geometry met invention. He imagined a circle divided into 360 degrees, inscribed with a radius of fixed length. For each central angle, he computed the chord, the straight line joining 2 points on the circle's circumference. These chord lengths, listed in increments of half degrees, formed the world's first trigonometric table. With them, any celestial triangle could be solved. This achievement transformed astronomy from descriptive to predictive. The heavens became calculable. The same method would one day be reborn in India as the Sine, in Arabia as the Jiba, and in Europe as the Sinus. But its seed was Greek, and its gardener was Hipparchus. Roads at night must have glowed with small lamps along the harbor, their reflections trembling on the water. Above them, Hipparchus traced invisible lines through the constellations, from the claws of Scorpius to the horns of Taurus, from Orion's belt to the star we now call Polaris. In those crossings, he established a celestial coordinate system, using the celestial equator and ecliptic as reference planes. Every star could now be given 2 numbers, right ascension and declination, or, as he named them, longitude and latitude of the heavens. This was an audacious concept. The stars, once worshipped as deities, were now plotted like points on a map. The cosmos became measurable terrain. For the first time, humanity possessed an address in the universe. Hipparchus also discovered a hidden connection between Earth's geography and the sky. By observing the altitude of a known star, or of the sun at noon, he could estimate his latitude on Earth, an idea that would later enable navigation across oceans. The same geometry that described the heavens could locate a traveler on the planet. Astronomy had become geography turned outward. In his comparative study of ancient records, Hipparchus drew upon the mathematical culture of Babylon. The Babylonians had for centuries kept clay tablets of lunar eclipses and planetary positions, written in sexagesimal numbers, base 60. The very origin of our 360-degree circle and 60-minute hour. Hipparchus recognized their numerical precision and fused it with Greek geometric reasoning. From that union was born the scientific method, observation verified by calculation. He criticized the poet Aratus, whose verses on constellations were beloved but imprecise. In his surviving commentary on Aratus and Eudoxus, Hipparchus compared poetic descriptions to measured positions, exposing errors. It was not malice, but discipline. Truth mattered more than beauty. Yet, in seeking accuracy, he achieved a beauty of another kind. The austere beauty of law and order written across the sky. From Rhodes, he observed several eclipses visible across the Mediterranean. By timing their beginnings and endings at different locations, he could estimate the moon's parallax, its apparent shift against the stars due to the observer's position on Earth. Using geometry, he deduced the moon's distance at about 59 Earth radii, strikingly close to the modern value of 60.3. His measure of the moon's diameter was equally precise. Even the sun, though farther beyond exact reach, he attempted to gauge through eclipse ratios. Each of these achievements demanded patience that few possess. The instruments had no lenses, no magnification. The observer's eye, steady as a compass point, was the sole detector. His accuracy depended on countless repetitions and the careful averaging of results. From such devotion emerged numbers that would guide astronomers for millennia. Hipparchus's star catalogue, Sinfiade, reconstructed from later citations, likely contained nearly 900 stars, each with coordinates and relative brightness. The faintest he could see marked the limit of human vision under pristine skies. He assigned 6 grades of brightness. The first magnitude for the brightest, the 6th for those barely visible. Even today, modern photometric scales honor his system. When astronomers say a star of magnitude 1 or magnitude 6, they echo a Rhodes night from 2100, years ago. His conceptual world was still geocentric. The Earth, at the unmoving center. But within that frame, his mathematics hinted at deeper truths. To fit observed motions, he displaced Earth slightly from the center of the Sun's orbit, acknowledging imperfection in the celestial order. This subtle deviation was a philosophical revolution. Perfection, it seemed, could accommodate irregularity. Nature did not obey geometry. Geometry adapted to nature. The influence of Hipparchus radiated quietly through centuries. His numerical methods, coordinate systems, and trigonometric approach were preserved in the works of Ptolemy, who called him most accurate of observers. In the Almagest, Ptolemy relied heavily on Hipparchus's data, often copying his star positions and verifying his precession rate of 1 degree per century, an estimate within a few arcseconds of modern values. Through Ptolemy, Hipparchus's mind entered Arabic science. Scholars in Baghdad, such as Al-Batan and later Al-Zarqal, expanded his trigonometry, replaced chords with sines, and improved planetary models. Yet every improvement began with Hipparchus's foundation. From Arabic translations, his legacy reached Renaissance Europe, guiding Copernicus, Tycho Brahe, and Kepler. Even when the sun displaced the Earth, Hipparchus's geometry endured. But beyond numbers and instruments, there was philosophy. The Greeks sought cosmos, order, harmony, balance. Hipparchus proved that such order could be found through measurement rather than myth. His universe was lawful, not capricious, predictable, not whimsical. The heavens, once divine, had become intelligible. Standing on the cliffs of Rhodes, he may have sensed that knowledge itself was a kind of worship. not of gods, but of truth. Each precise angle, each recorded star, was an act of reverence. The universe revealed itself to those who cared enough to measure. In later generations, poets forgot his name, but sailors followed his coordinates. Mapmakers borrowed his projections. Mathematicians extended his chords. When the first mechanical astrolabes were built, they encoded his geometry in brass. The device that guided travelers beneath the Islamic sky was, in essence, a handheld echo of Hipparchus's spheres. Even the idea of latitude and longitude on Earth traces partly to him. By relating celestial positions to terrestrial ones, he turned astronomy into the architecture of geography. Centuries later, when cartographers drew the grid lines of the world map, they were unconsciously drawing the sky's reflection. Hipparchus's invisible framework made visible on parchment. At the close of his life, the old astronomer must have known his calculations would outlive him. Perhaps he imagined some future mind, born in a world transformed, still measuring the heavens. He could not have guessed that satellites would orbit the Earth carrying his coordinate system, or that spacecraft would navigate by the very trigonometry he invented. When he died, sometime after 120 BC, the scrolls of his observations may have been left in the libraries of Rhodes or carried to Alexandria. Fires, wars, and centuries of neglect erased them. Yet not all was lost. Knowledge, once shared, never entirely disappears. It migrates through memory, translation, and rediscovery. More than 2,000 years later, that migration came full circle. In 2017, scientists re-examining the Codex Climaci Rescriptus, an ancient palimpsest in the British Library, found hidden Greek text beneath Christian writings, coordinates and star descriptions matching Hipparchus's era. The faint traces of ink, analyzed with multispectral imaging, revealed what might be fragments of his lost catalogue. The numbers aligned astonishingly with modern celestial positions, confirming that he had indeed mapped the heavens with scientific precision. In those ghostly letters, written by hand before Christ was born, humanity glimpsed again the birth of science. The discovery turned what had long been legend into fact. Hipparchus truly was the first to chart the stars as a mathematician rather than a myth-maker. The revelation closed a circle, not the geometric one of his chords, but the human circle of curiosity fulfilled. Across millennia, the same desire that once drove a Greek on Rhodes to measure the sky had found its echo in digital light, deciphering ancient parchment. If part one was the awakening, the night when man first measured the stars, then this is the geometry of faith. Faith that truth survives. Each coordinate written on those crumbling pages is a monument stronger than stone. As the 2nd century before our era deepened, the island of Rhodes began to drift quietly into the margins of history. The bronze colossus that once towered over its harbor had long since fallen. The city's bustling markets still echoed with the cries of traders. But the tides of empire were shifting. Rome was expanding eastward, absorbing the fragments of Hellenistic kingdoms, drawing Greek learning into its vast orbit. Amid this changing world, an old astronomer continued to work by lamplight in his study overlooking the sea. His eyes, dimmed but steady, still traced the slow movements of the heavens. This was Hipparchus of Nicaea, the man who had measured the stars and, in doing so, measured time itself. The air in his chamber was heavy with the scent of oil and parchment. Wax tablets, covered with trigonometric tables and geometric sketches, lay scattered beside a polished bronze astrolabe. Each mark, each number, was the residue of countless nights beneath the sky. Outside, waves brushed against the harbor walls. Inside, Hipparchus's stylus whispered across the wax as he adjusted yet another figure, refining, correcting, pursuing a perfection that perhaps only he could perceive. He had spent decades comparing ancient records with his own observations, aligning Babylonian star lists with Greek geometry. And now, in the final years of his life, he turned his thoughts toward eternity, to what would endure after he was gone. He began to compile what he called a catalogue of the stars, a map of the heavens as seen from Earth. It was not the first of its kind, but none before had reached such precision. Using a simple sighting instrument and his own trigonometric system, Hipparchus calculated the positions of more than 800 stars, noting their brightness and celestial coordinates. To him, it was not a collection of names, but a kind of cosmic architecture, a frozen reflection of the moving firmament. He measured their declinations and right ascensions, anchored them against the ecliptic, and in doing so, established a framework that astronomers would use for the next 2,000 years. There is a strange humility in such work. To measure the infinite from a single island, to fix the stars with lines drawn in sand. Yet Hipparchus's genius lay not only in observation, but in doubt. As he compared his results with older records, he noticed something extraordinary. The positions of certain bright stars, such as Spica and Regulus, no longer matched those recorded centuries earlier by Babylonian astronomers. They seemed to have drifted, slowly but unmistakably, along the celestial sphere. At first he suspected error, but his calculations were relentless. Night after night, year after year, he confirmed the same displacement. The heavens themselves were not fixed. The axis of the Earth was moving, precessing, tracing a slow, circular wobble across millennia. This revelation, now known as the Precession of the equinoxes, was one of the greatest discoveries in the history of astronomy. It meant that the coordinates of the stars were not permanent, that the very sky changed over ages of time. The constellations would rise in new positions. The pole star itself would shift. To recognize such a motion, invisible within a human lifetime, required both mathematical brilliance and an almost spiritual patience, a faith in the continuity of time. Hipparchus had found a rhythm of the cosmos that no mortal would ever see completed. He never spoke of it in poetic terms. His surviving notes are terse, methodical, cautious. Yet behind the geometry lies awe. He must have looked up at the midnight sky, realizing that the heavens were turning not just nightly, but through ages, that every civilization before him had lived beneath a slightly different map of stars, and every civilization to come would inherit another. In that realization, the ancient Greek world brushed against the modern sense of cosmic time. With Precession, Hipparchus gave future astronomers a key to the deep calendar of the universe. It allowed later scholars, from Ptolemy in Alexandria to Copernicus in Poland, to correct and realign celestial coordinates, to measure centuries through the slow drift of equinoxes. The very tilt of Earth's axis, invisible yet eternal, became a marker of history itself. But his influence did not end with astronomy. Hipparchus's tables of chords, the ratios between sides of triangles and the circles they inscribe, became the foundation of trigonometry. Though he never used the term, his system of dividing a circle into 360 degrees and describing relationships between angles and lengths was adopted by later Greek, Indian, and Islamic mathematicians. From his tables, Scholars in Alexandria would derive the sine and cosine functions still used today. Every engineer, navigator, and physicist who plots an angle or trajectory is, knowingly or not, walking in the footsteps of Hipparchus. In Rhodes, however, his passing went largely unnoticed. He left no school, no disciples to preserve his notebooks. The island grew quiet, and over time the manuscripts were carried away to Alexandria, where they would later form part of Ptolemy's great synthesis, the Almagest. For centuries, Hipparchus's name was overshadowed by those who built upon his foundation. Yet his unseen hand guided every astronomical model that followed. Ptolemy's star catalogue, Copernicus's heliocentric calculations, even Newton's gravitational equations all trace their lineage to the trigonometric geometry first forged on a lonely island in the Aegean. Centuries after his death, his star catalogue was thought lost until, in the 21st century, fragments resurfaced in an unexpected form. Scholars examining the Codex Climaci Rescriptus, a medieval manuscript palimpsest, discovered beneath layers of erased text a set of astronomical measurements written in Greek. Advanced imaging revealed that these were none other than coordinates, recorded by Hipparchus himself, the oldest known star map ever found. After 2 millennia, his observations had re-emerged from the shadows of time, still accurate to within a single degree. The precision was staggering. What he had seen with the naked eye had endured through empires, languages, and faiths. It was as though the universe had kept his secret safe, a cosmic signature left for humanity to rediscover. And so, across the centuries, Hipparchus's legacy quietly expanded. In Islamic observatories from Baghdad to Samarkand, scholars refined his trigonometric methods. In Renaissance Europe, astronomers used his precession model to update celestial atlases. When Tycho Brahe built his giant sextants in Denmark, he was perfecting Hipparchus's geometry with brass and wood. When Kepler described the motion of planets in elliptical orbits, he relied on trigonometric principles rooted in the Greeks' tables. Even in the modern age, as satellites chart the stars with atomic precision, their data are still expressed in the same celestial coordinates that began with him. In a deeper sense, Hipparchus also changed how humanity conceived its place in the cosmos. Before him, the stars were eternal symbols, myths of gods and heroes frozen in the sky. After him, they became objects of measurement, governed by laws that the human mind could comprehend. He turned the heavens from legend into geometry, from poetry into pattern. Yet, in doing so, he did not diminish their beauty. He revealed it. Standing at the edge of the ancient world, Hipparchus bridged myth and mathematics. He was a craftsman of time, carving structure from infinity, showing that the universe could be both mysterious and knowable. The Greeks called this pursuit cosmos, not merely the physical heavens, but the order that unites all things. To measure the stars was to seek that order, to glimpse the harmony between the human mind and the universe it observes. Perhaps in his final nights on Rhodes, as he watched the constellations drift above the sea, Hipparchus understood that his measurements were only beginnings, coordinates in an endless dialogue between light and thought. His life's work would not survive in temples or monuments, but in the quiet endurance of numbers, in the invisible arcs of time. The stars he catalogued would shift, but the pattern of inquiry he began would endure as long as humanity looked upward. Time moved on. The island's harbors silted. The library of Alexandria burned. Empires rose and fell. Yet, above them all, the precession he discovered continued. The slow, eternal turning of Earth's axis, tracing a circle through the ages. Every 26,000 years, the heavens return to the same point, and perhaps somewhere in that infinite cycle, his name is spoken again under the same stars he once measured. Today, when astronomers map the Milky Way or calculate the orbit of exoplanets, they inherit a tradition born in the flicker of an oil lamp on a Greek island. When a student learns trigonometry, they are echoing his calculations, each sine and cosine a quiet remembrance of the man who sought precision in the sky. And when we gaze upward, marveling at how small we are beneath the universe, we participate in the same act of wonder that guided Hipparchus's hand 2,000 years ago. The ancient Greeks believed that knowledge was a form of reverence, that to understand the cosmos was to honor its beauty. Hipparchus lived that belief. His geometry was a prayer written in numbers, his astronomy a hymn to the order of creation. He did not seek fame, only clarity, and in that pursuit, he found something eternal. As the final embers of his lamp faded and dawn returned to the horizon, the old astronomer set down his stylus. The waves of the Aegean glimmered silver under the rising sun, and the stars he had charted vanished into the light. Yet their coordinates remained, silent, exact, immortal. And in that silence, the voice of history whispers, "The sky is never still. The stars move, the earth turns, and across the vastness of time, one man's measurements continue to guide our gaze." The father of trigonometry, the discoverer of precession, the forgotten astronomer who measured the stars, Hipparchus, the man who taught humanity to count the heavens,